All right, welcome to the OpenXR update. So ahead of us, we have 1 hour of presentation. So first, I will be giving the updates from the working group. Then we have Mark here that will give an update on GFX Reconstruct, which is a capture and replay program that actually added support for OpenXR, but we're going to hear more about that. And then we're going to join together and give a summary, and then we're going to take Q&A. I am Denny Rönngren, and I'm the vice chair of the OpenXR working group. Also, I work for Varjo, one of the headset makers that makes an ultra-high resolution XR headset. There are some assumptions that you know a little bit about OpenXR, since this is an update. But if you're completely new to OpenXR, we have some resources in the end, some really nice tutorial that you can try out yourself later. Good. Let's get started. So let's see. All right, covered that already. Slides are going to be available afterwards and recordings, so you don't need to take notes unless you want to. Good. So my presentation will be first, what is OpenXR, the ecosystem support, a little brief about the history of OpenXR, then a really exciting update that we do have, and this is spatial compute through Spatial Entities for OpenXR. This is actually the big thing that I want you to remember if you remember just one thing, and GFX Reconstruct, of course. Some mentioning on multi-app that we are discussing in the working group as well, and then GFX Reconstruct summary and Q&A. So first, OpenXR, what is it? So OpenXR is an open, cross-platform, high-performance API between devices and platforms. This essentially means that you can write code that runs across all compatible devices. So no need to change any code as long as you are sticking to the core standard. Of course, you need to recompile if you are supporting Android or Windows, but code-wise, most of the things should be okay. Before OpenXR, we have the story here on the left-hand side. Yeah, left-hand side. So before OpenXR, we had headsets were available, different SDKs were available. Everything was kind of great, unless you wanted to write an application that ran across all of the devices. So then you needed to integrate support for many SDKs. And the bad thing after that, when you were done, maybe there was a new headset coming up. And maybe they had a new SDK that you needed to integrate. And then, you need to reopen your app for development again. It also might be the case that if you're a game studio, that, the game wasn't under development anymore, leaving, the new headset users without the ability to use your game. On the right-hand side, you have OpenXR, and here we have a single application interface. So this is the one that you should target. And as long as you are doing that, everything is easier. So this actually broadens your reach of your application while keeping cost low. And by you, I mean, if you have your own rendering engine, then you work with low-level OpenXR. But many of the big game engines, or all of the big game engines, they have done the integration for you, so you can start creating content directly. But it might be times where you need to engage with OpenXR interfaces, even if you are using a game engine. It might be the case that the engine doesn't have support for the extension that you want. And then typically there are hooks so that you can capture calls and create new functionality. Good. And a short history here of OpenXR. So the working group was formed in 2017. most of the companies came together at that time and decided that we wanted to grow the pie of compatible applications and make the life for developers easier. A couple of years afterwards, in 2019, 1.0 spec was released, actually at SIGGRAPH in Los Angeles. And at that point, we actually had 2 preview OpenXR implementations for headsets ready. And we actually did the live demo at SIGGRAPH, showing that the spec was actually functional and it was possible, to use it. For the years after, hardware vendor were working on OpenXR implementations for their headsets, and also the big game engines adopted OpenXR and started to support it. A lot of extension came about at that time as well, because everybody wanted to do feature parity with their own native APIs that they had previously. And also we were listening quite a lot to the developer community and wanted to please them as well. In 2024, the first core spec update was done, and here that's the 1.1 release. So here, mainly, like a few extensions graduated into the core specification for weighted rendering and handling of input profiles for hand controllers and such, and a few other things. And you can see 1.2 doesn't have a date, so we don't have a fixed date for it, but you don't need to worry. We are very productive at the moment, and we are exploring new features like body tracking, haptics, audio, spatial compute through Spatial Entities, and also multi-app support. The working group is very healthy, and there's very good collaboration. So I'm not going to go through all of this, but here you see the conformant devices that we have today, many names that you do recognize. Android XR is one new runtime that adopted OpenXR at the end of last year. So that's good to see. And also I would like to point out Acer and Sony, who does have spatial displays that you put on the table. And they can actually produce 3D content without wearing glasses. And I think this is really interesting because it shows that OpenXR can support a multitude of form factors. And also you can see on some of the headsets are mixed reality headset where you have RGB cameras that is capturing the environment and compositing in the real world into VR. And we are able to support that one actually since 1.0 of the spec. So going to the game engines, you can see Unreal, Unity, and Godot support OpenXR, and they support OpenXR 1.1 and 1.0. So it's really great to see that they're keeping up with the standard. And then we have Autodesk, we have NVIDIA Omniverse, NVIDIA Cloud XR, which is NVIDIA's cloud platform, and also the web browsers that are supporting WebXR. So Chromium was one of the first adopters of OpenXR, actually. Meta released a simulator as a library that actually runs on the PC and the Mac, which is interesting. And then we have StereoKit as well. And there are more engines. Many applications have their own engine, and we are definitely seeing that the vast majority of custom engines are going to OpenXR as well. So companies supporting OpenXR, these are essentially, like the members of the working group. All right, do we have any hardware vendors in the room that doesn't have an OpenXR runtime? There were, maybe. So if your XR headset or spatial display doesn't support OpenXR today, there is actually a open source project, Monado, from Collabora, which is a complete OpenXR runtime that is modular, that allows you to essentially convert your drivers into, or plug in your drivers into the Monado runtime, and then exposing everything through OpenXR. So it can be, like a good way of bootstrapping your OpenXR runtime development, actually. The most important thing here is that the purple layer here, that's the thing that we are testing. And in the working group, there are companies that are using Monado, but then there are many companies that have their completely own OpenXR runtime as well. So the choice is there. The group wanted me to present also what we have done since the last year. It's a lot of stuff, so I'm not going to cover everything in great detail here. So I'm going to focus on a few other things, so I'm going to flash the slides. 2 Kronos extensions we did, and also 5 families of cross-vendor extensions. And then we have a multitude of vendor extensions as well. We did some registry and XML schema enhancements, and this might sound a little bit weird, but this is the tooling that we use in order to generate the headers, generate the spec, work on the spec, and all of that. So we have done that. We added, for testing and CI, we switched to Catch 2. And also we added Mac to the CI environment, since we currently also have a graphics binding for Metal. And validation and SDK improvements, there's a lot of things there, various bug fixes, logging improvements, and improvements for running on Android and running layers and whatnot. But then we have the last thing, and I find this very engaging. So like in the ecosystem, the working group came together since we are paying to be members, and it also costs money to run the conformance suite. Then we collect money, and we have a budget. And part of the budget we actually decided to put to implement features in the Godot game engine, or actually hire a consultant, Bastian, to do that. And that actually turned out to be a great success. And the reason why we wanted to do this is for some of the extensions that we were working on, then we wanted to see them implemented actually in a real game engine to iron out specification bugs and stuff. And it actually happened. So at least 2 of the extensions we were able to fix issues before releasing it to the public. And also it's great to see more XR support in Godot. So going to a few extensions here. So the first one is XR KHR Metal Enable. And this is a graphics binding for Metal. Interesting. So the driving force for this one was actually one of the member companies wanted to have a simulator that could run on Mac and PC. And if you run on Mac, then you are using Metal as rendering APIs, and then you need to be able to submit Metal buffers to the runtime. So we came together and we worked on adding this. So today we have Kronos extensions for Metal, Vulkan, OpenGL, and D3D 11 and 12. Since the Metal extension is not perhaps widely used, not every member supports it, of course, we quickly realized that we need to secure this with CI, so we needed to extend the CI for Mac. It was actually a little bit of a hassle to do that, but we succeeded in the end. And also we added support for Metal rendering in Hello XR sample. So that about that, and then we can move to render model. And render model is actually an extension for the application to know the mesh and the textures of the controllers that you are holding. So typically, if you do an VR application, the user want to see their controllers. And this extension supports reading out the controllers dynamically. And they are being read out as GLTF assets. And there are named nodes that the game engine is responsible for animating. But there's also an array coming out with the values for all of the nodes, the transforms, and also the visibility. So the spec itself is quite long, I would say. But just taking it easy and reading it through, it's actually not that hard to add support for that in a game engine. And I'm super happy to share that this is a cross-vendor extension, of course. It was a few vendor extensions available to do this previously, but finally we do have a future-proof cross-vendor extension. So if you have done your application, you have support for this one, and maybe in a couple of years a new headset is being released that has new controllers, you should be fine because you are reading the controller's visualization dynamically. The third thing that I wanted to point out is the environment blend mode alpha blend. And this is a way of enabling mixed reality. Mixed reality is for VR headsets that has outward-facing RGB cameras that can capture the world. So you can see your environment intermixed with the VR experience. So previously, there's been some vendors that didn't support this blend mode, but as of now, everybody is on board. So this is the most compatible way of enabling pass-through for OpenXR devices. And we actually needed to ship an extension for inverting the alphabet. And this is important for mobile platforms where you can't, do many conversions because the headset is very sensitive to thermals and battery use. So this was one of the core enablers that allowed everybody to get over the hump. If you're interested to see which extensions that runtimes are supporting, there is a OpenXR inventory, and there's a link here, and there you can go and see. And we are also adding which extensions that game engines are supporting as well, game engine and game engine plugins. So we hope that this is a good resource and it's community driven. And by community driven, it essentially means that some individuals in the group is spending sometimes a little bit private time on trying to support this one. We take pull requests, so if you see that something is not there, let us know. If you want to change the layout or have some suggestions there, we can take pull requests on that one as well. All right, so let's go to the big star, Spatial Entities. And this is Spatial Compute. The extensions were released in June 2025, so these are brand new. There are 6 cross-vendor extensions. We did a blog post about it, so you can go there and you can see what the companies are saying about it. So what is it? On a high level, it's a detailed API for the headset to reason about the user's environment. Many vendors had their own APIs to do this previously. This has been a big collaboration effort in the working group, both from the hardware vendors and also from game engine perspective. So quick adoption is expected. Phase 1 is out now, these 6 extensions, but there's really good momentum on providing more data through this framework. So the extensions are about spatial anchors, and spatial anchors is for application to be able to create an anchor point in the real world, to be able to place a VR content there, and then the headset can actually take that point and keep track of it over time, thereby relieving quite a lot of the burden on the game engine, while providing, like the good spatial understanding that an XR device have. We have spatial markers, which are QR and Aruco markers, to name a few, and those have also a position in space and extend, and you also can get some data from the markers as well. And they are also sometimes used to anchor virtual content. We have plane detection. So with mixed reality and augmented reality, you usually want to know where the walls are, where the ceiling is, floor, maybe the table, the desk. So this is what the plane detection extension does. Then we have persistence. And for anchors, you can imagine if the user puts out virtual content and lock them to specific positions, quits the app, and the next time he starts the app, probably the content should be in the same place. So this is what persistence does. It actually tells the runtime that this is something that I want to keep track of for the next session as well, and then the runtime will resurface that at the next run. And then we have persistence operations, and that's about deleting components and stuff like that. All of this is part of a framework, and since it's part of a framework, there's more to come very soon, I would say. I'm not going to go through this. I think I'm a little bit short of time, but this is the general flow that you use in order to work with spatial entities, like essentially 4 steps, and it's not that many function calls. Here it actually looks like it's more function calls than it is, because it's using our futures extension, which is asynchronous programming. So some of the calls are actually one start and one end call. And now I'm going to show a video from Godot, who actually, and the Godot game engine actually has support for all of the extensions today. So this is like a preview video from with it running in one of the headsets actually. Okay, so Bastian is talking here, and he's saying that he have these anchors that he puts out, and to the anchors he put virtual content. When he moves the object, he actually creates a new anchor. All the anchors are being tracked by UUIDs, and this has been created in the previous session as well, so it's already set it up once. And it's also showing the physics here with dropping plushie, so it lands on the desk. You see, first the object was here, he dropped it, there was an anchor there, and then it landed on the table, and then he created an anchor on the table. All right, good. So switch gears a little bit, multi-app. So OpenXR 1.0 first focus was on immersive applications, and immersive applications are applications that has infinite render bounds and completely replaces your real reality. Usually one runs at a time, although the spec doesn't forbid having two immersive app running at the same time. But in practice, usually just one app is running. Today, we have recognized that there's more interest of having a broader set of applications, which may run in parallel. So the goal now is to enable running multiple simultaneously visible OpenXR applications. And the key focus is to work out the application model, because that needs to change a little bit, and then prove it out. And the goal of all of this is to enable a spatial window manager for headsets. So instead of having a console-like experience, we have one app that completely replaces everything. We want to enable the members to build like a window manager that can handle multiple applications. And experimental headers are being worked on, so stay tuned for those. A little bit about what's coming soon. So hand tracking and body tracking we are working on. There's intense discussions on like taking that to the next level. We are working on expanded haptic support to be able to have haptics for immersive experience going beyond PCM waveforms, like the buzzers and all of that. And then also enhanced handling of spatial entities. And there's an intense work on providing more components through the spatial entity framework. And then I also mentioned multi-app ... And here are the resources that I talked about in the beginning. So we have the OpenXR SDK, and that's one of the things that we are producing. We have the reference pages, the reference guide. And that is kind of developer documentation. It's usually very technical, so it might not be the best way to learn about OpenXR. But if you need to implement it in your engine, or if you're looking up a specific extension, this is where you want to go. But then if you are new to OpenXR, we have a very nice tutorial and that can run both on Android, Linux, and Windows. So you can create an OpenXR application from scratch in Android Studio or Visual Studio. We also have the conformance test suite, and this is something that all the hardware vendors are running to make sure. And this is an automatic test framework that exercises the APIs, so that we can say that all headsets are behaving the same, where we have test coverage at least. And also we have supporting community forums on Discord, on the Kronos forums. We have an issue tracker on GitHub. So if you write an issue on GitHub, we automatically get internal issues and we take them up at our weekly meetings. If you're developing OpenXR resources yourself, let us know. Maybe we can help you promote your OpenXR resource, or if you are providing documentation that we don't know about, please let us know. That's that. Thank you.
Hi, thank you so much. My name is Mark Young. I'm going to talk about some work that John Zuloff and I did to capture and replay OpenXR and Vulkan content. Just out of curiosity, how many of you have used GFX Reconstruct before? Okay, just a few people? Well, not too bad. Okay, so I'm going to go over a brief overview of what our tool, which is open source, GFX Reconstruct does. I'm going to talk about how we implemented the OpenXR proof of concept in it, go over some challenges, and you can read most of the other slides. I won't go into too much detail here. What this is not going to be, though, is this is not going to be an in-depth tutorial. So don't worry, I'm not going to put you to sleep with that lunch you had earlier. If you do want a tutorial, Brad Grantham, our architect, actually has several online, and I'll point those out to you in the future. So GFX Reconstruct is kind of an odd thing. We were participating in the Vulkan working group early on, and we attempted to do a capture replay tool first called VK Trace. Unfortunately, the code gen was rather clunky. It was not performant. It was not very portable. And so in 2019, we kind of decided this isn't working. Let's start again from scratch. And thus we got GFX Reconstruct. The purpose of Graphics Reconstruct is to capture the API calls of your application. So it's not capturing your AI, it's not capturing your audio, not capturing your game mechanics. It's purely focused on recording what's necessary to encapsulate your application's usage of an API. That includes API commands, that includes memory for buffers, textures, things like that. We get the memory information actually using various OS techniques. Also, we have to capture certain things like OS-specific things like hardware buffers, Android hardware buffers. This content that we capture is recorded into a binary file. The benefit is we can internally also use compression. What we really push this for is, here's an example. You have your application. Like maybe you're making the new game, big game, but you have a bug on level 3, takes you, 5 minutes to get to. How do you send that to a hardware company for debugging? Well, you capture with our tool and you send it to them, and you're sharing a binary, not your application. And so some enthusiastic intern can't decide to leak your game out to the public. So what does Graphics Reconstruct currently support? Currently we support Vulkan and D3D12. And I'm not talking very simple. We support advanced functionality like ray tracing and mesh shaders. We update pretty regularly. We'll pull down the Vulkan headers or the Agility SDK. And since we have code generation, we can generate a lot of the API entry points fairly quickly. We also run both an external and internal CI system so that we can make sure we maintain a good quality product. Graphics Reconstruct kind of executes with certain principles in mind. Obviously, you can read them: fidelity, integrity, portability, and performance. Our priority, honestly, is to try to reproduce your application as it behaves. And so if you have a bug, we want to be able to reproduce that bug. If you behave correctly, we want you to be able to reproduce correctly. We do make trade-offs, especially when you want to make something that's portable. You have to rebind memory and various things like that to work on one system versus another. But in general, our goal is to try to follow these principles as close as possible. So what is it useful for? As I mentioned, you can share bugs. You can do a regression testing system with it. You can actually take those capture files that we generate and run them through a tool that will generate a parsable, human-readable JSON file. And you can process that file for API usage information. You can even set it up to, I want to keep repeating this one frame over and over again, so you can do performance profiling on that frame. While many of you may not have directly used Graphics Reconstruct, behind the scenes we're actually becoming the engine for a lot of profiling and debugging tools. So you might actually be using us and not knowing it. When I say Graphics Reconstruct, what I'm really talking about is a collection of tools. And the ones I'm going to be talking about are our capture portion, which I've kind of alluded to, and then a replay portion. We also have a simple tool called Info, which will give you a high-level overview of what content is in a capture file. And we have the Convert tool that I also mentioned, which will generate some JSON output based on your binary data. So now for OpenXR. About a year and a half ago, I believe, we were approached to implement OpenXR support by a very generous client. We ended up implementing OpenXR 1.1. I believe it was 1.1.37. I could be wrong. We have limited support because we have only been able to test a certain amount of applications. We also only support Vulkan. For those of you who don't know, OpenXR does not have a rendering engine itself. You have to hook it up to another rendering API. That could be D3D12, that could be Vulkan. So right now we only support the Vulkan rendering API in conjunction with OpenXR. And as I said, we only have a small set of verified extensions. We co-generate all the entry points, especially all the ones that were up to the point of the version of the headers we used, but we haven't been able to verify them because we've only been able to run a certain set of test apps. We do have a bug which currently prevents anything but single-threaded apps from running. And another caveat is if you pull down the Vulkan SDK, you get Graphics Reconstruct. Because we consider OpenXR support a proof of concept, we don't enable it in the version that's sent out with the SDK. You have to build it yourself. But as I mentioned, this is open source. I'll give you a link to the repo, and it's enabled by default in that repo, so you can try it out very easily. So what are some of the challenges we ran into? We've obviously been very involved in Vulkan, and so even though Vulkan and OpenXR are both created by Khronos, they have different, basically, creators, different parents almost, with the working groups. So OpenXR introduced atoms and opaque values in addition to handles. That wasn't too bad. We just handled them like handles. They introduced parent and child structures. That kind of broke our code gen. We had to rework our code gen in order to properly handle the relationship. Whenever you would get into an entry point, you'd have to know, I'm really expecting this child at a certain time. You could create your own instance and Vulkan device and pass them into OpenXR, or you can say, OpenXR, you create an instance and device and send it back to us. Have to worry about that. Enabling OpenXR API layers on a headset, that's difficult. Has anyone tried that before? It's not really that easy, unfortunately. For those of you who don't know, OpenXR has baked into it a session lifecycle. You have a sequence of events you have to do. You wait for something to happen and then you can do something else. Because our capture file is so dependent on what's happening during capture time, we're baking in the lifecycle that occurred at capture time, and we had to work around that actually during replay time. We found that when I wrote the replay app, I would encounter issues, and unfortunately, the validation layers were insufficient sometimes. And so I ended up actually reverting back to using our own JSON converter output. We ran into this problem. We call it a reentrant problem. I think John Zuloff actually called it this. What happens is, as I mentioned, OpenXR does not have a rendering. It does not perform rendering itself. However, it does compositing. So it will use whatever rendering API you provide to do the composition for you. So in this case, your application makes Vulkan calls. It makes an OpenXR call. Internal to the OpenXR runtime, it makes Vulkan calls itself and then returns and then does more Vulkan calls from your application. Unfortunately, we don't want the Vulkan calls from the OpenXR runtime because when we replay, we're going to get those same calls. And if we're trying to mimic what the runtime was doing, you're going to get improper behavior. So what we do is we currently disable recording once we enter OpenXR, perform the OpenXR calls, and then re-enable recording, record the OpenXR content, and return. So very briefly, how do I enable this on a MetaQuest headset? Well, you recursively pull down our repo because we rely upon external repos like Vulkan headers, OpenXR SDK, and so that just pulls everything down. You don't got to worry about it. And then we wrote a top-level file called howtometaquest.md that's in the repo. And overall, it covers everything from installing, building, and running the graphics reconstruct with your application. Two things I'd like to point out. If you're using Gradle, you have to add graphics reconstruct as a dependency. And this goes back to the fact that because of the way the headsets are, you have to define an OpenXR API layer as part of your application. And so you have the JSON manifest file that we insert in, as well as the dynamic library for graphics reconstruct. Also, if you're building a release application, you need to turn on debugging because the underlying OS will not connect the Vulkan layers to the application unless it's debuggable. So roughly, this is how graphics reconstruct works. We're running really fast on time, so I'll try to talk fast. Basically, the OpenXR content is captured through an OpenXR API layer. The Vulkan content is captured through the Vulkan implicit layer. We still pass everything down to the implementation and runtime, and meanwhile, we're recording it to a binary capture file. Pretty straightforward. So here's an example of I just captured a capture file running an application. What if I run info on it? Well, this is an example where this is OpenXR tutorial chapter 4. It says it right there. It says, oh, by the way, I did use LZ4 compression, and you got 240 frames in this capture file. It was captured on an Adreno. And then you got more information too at a very high level, how many allocations, what sizes they were, what graphics, what pipelines you were using. This says one graphics pipeline, no compute, and no ray tracing pipelines. And then finally, some very basic brief information right now for OpenXR. So not very useful, but it's good to know, hey, it did capture OpenXR content. The convert output is going to be more useful for most people because it's going to do a human readable breakdown of all the API entry points encountered, including Vulkan and OpenXR, so you can kind of see the interleaved behavior of all those commands. So in this case, you've got an XR poll event. It's for a reference space change pending event on a stage, and it succeeded. So you can tell a whole bunch of information just by running this tool really quickly. And again, you can use this for API usage analysis. Replay is pretty simple. It just takes the commands, reruns them through the Vulkan implementation or the OpenXR runtime. Yes, this one's correct. One of them actually have, yeah, this one's wrong. It should say OpenXR runtime and Vulkan implementation, sorry. So how do I see my results? Well, you can wear the headset, but we don't recommend that. The reason I say that is when you're capturing, the person might be looking around. During replay, we do some things that could make you sick if you're trying to watch the replay. So what we actually recommend is you use something like the Meta desktop app to cast the headset images to your desktop screen. It just makes it easier and no cleaning up afterwards. So what do we have to do to make replay work? For those of you who don't know, whenever you create like a Vulkan instance or an OpenXR instance, you're not guaranteed the same value every time you call it. So the capture might have had value A, your replay has value B, so we have to remap the handles at replay time. Of course, we have to fill in memory. If you've allocated memory, we're doing that capture behind the scenes of what's in the memory, and then so we fill it in using metadata commands at replay time. Of course, since it's a layer, you're getting an XR create API layer call, API layer instance call, not an XR create instance call, but that's pretty straightforward. We also do this thing called virtual swap chain. For those of you who don't know, whenever you capture with a swap chain, let's say you have 3 images. You're not guaranteed to get those images in order 1, 2, 3, 1, 2, 3, 1, 2, 3 all the time. You could get 1, 2, 3, 2, 3, 1, 3, 2, 1 in some whatever order. But that order also is baked into the capture file. So we have to virtually simulate the behavior of the capture swap chain during replay. Certain OpenXR commands use times based on certain events. So we actually have to figure out what those relative differences are from various points and update those for the replay for everything to render correctly. Here's where we actually cause the nausea if you're wearing a headset. Again, the person's looking around a lot during capture. If I look straight ahead during replay, what I would end up seeing is a curved billboard moving, tracking the original, person's headset, right? Instead, what we do is we remap that headset view so that it looks wherever you're looking. Of course, that's going to be jogging around a lot depending on what the person did. But we figured you wanted to see what the person saw. Again, the OpenXR lifecycle is baked into the capture file. So on the replay, you might get events in different orders. You might get no events that you had before. You might get new events. So you have to handle those. And some of those new events are actually caused by the last bullet point. Unfortunately, we can't read what your application Android manifest file is beforehand. So we don't know what permissions you're enabling, like pass-through, right? So we kind of just had to guess and enable everything we could. We kind of just threw the kitchen sink at it. And so everything is enabled as much as possible in the replay application. The issue we're running into with multi-threading goes back to that reentrance issue, right? We're disabling recording during the OpenXR call and then re-enabling it when we're done. Well, if you have multi-threaded Vulkan, we just blocked some of your valid Vulkan calls. So that's going to have to be something that's get resolved soon. Future improvements, it'd be nice if we could test more applications so we can validate more extensions on more headsets. What would be nice is to go in the future and add in a screenshot ability at both capture and replay time. So you could say, this is what I captured, and I'm seeing the exact same thing on replay. Be very easy to verify. And then there's another feature that we have for D3, D12, and Vulkan, which is called trimming. Let's say, again, your bug happens after 20 minutes. You don't want to send this giant data file to NVIDIA or Meta. So what we allow is we allow you to trim down to a certain smaller set of frames, but that includes a lot of state tracking that needs to be done. So here's a list of the applications we verified. I don't know if any of you were here, but at AWE, we demoed a version of the OpenXR Provider v2 hand painting app. And we've run it not only on a MetaQuest, but we do some testing with Monado on desktop. So we've done Windows and Linux Monado on desktop. And here's a link to the videos. Again, since they'll be in the slides, just pull them down. Brad Grantham, he's back here, back there. He's our architect, really sharp guy. He made those videos. I highly recommend them. Sources on GitHub. And again, I highly recommend How to MetaQuest Markdown. And in summary, GFX Reconstruct continues to grow. Again, it's a proof of concept for OpenXR support, so it may not handle all your cases right now, but help us verify the functionality is there. And I just want to point out real quick, we will put our own presentations up too. There's a LunarG website. The thing I want to really point out, which we'll be having later in the back, is Cosmic Crisp. For those of you who don't know, it's a Vulkan on metal layer, I guess to say, almost like a driver. And so we're highly in progress with trying to make that work great, and we'll be having demos at the back. So I'll let you take over. Thank you very much.
Yeah. All right. Summaries, nice summary of GFX Reconstruct. And okay, first thing that we always say, if you're a hardware vendor, consider joining OpenXR to help drive the future of XR. Specification for Spatial Entities has been ratified and is available online. Hardware vendors are implementing, game engines are adopting, and this is a framework, so stay tuned for more extensions to come. Multi-app discussions are ongoing in the working group. Keep your eye open for foundational extensions. And these are designed not to constrain member company innovation, and they are intended to move OpenXR to from a single console era of applications to more like a window manager era. Kronos OpenXR funded development on Godot, so if you use Godot, go and try. And also we have LunarG GFX Reconstruct supports OpenXR today in preview, and I got to try it myself. So with that, we open up for questions. I can't say anything, by the way. The lights are very sharp. Ah, there we have something. Ah, you can go to the mic. Yes. Yeah.
We just want to make sure we get this. Can we get the mic turned up a little bit, please? Testing. Testing. There we go.
Yeah. Pretty interesting stuff, this OpenXR thing. One thing that I would like to ask is, like, for like VR stuff, for like the more complicated multiplayer-ish VR stuff, like VR chat and the like how would that work with Spatial Ink, or is that? I mean, I'm not involved with them, but
Oh, okay.
but I wonder how how this might be of relevance to people who are trying to develop VR applications for like multiplayer stuff.
Yeah, it's a really good question actually. So OpenXR sits, on the bottom in the software stack. So like the typical thing is that applications are developed in a game engine, and I don't actually remember which game engine VRChat is using. But the flow works like this. The game engine needs to add support for extensions, and then the game itself needs to be updated to take that into account. So usually there's like a delay, and I think the delay is going to be a little bit shorter this time until all the game engines are on board.
I was just wondering. I don't have any. Yeah, I don't really have anything to do with game development. My major is actually cybersecurity, but.
All right. Thank you so much.